Thank you, and thank you for inviting me here. It's nice to be in Warsaw again. My title is a short version of this more modest title, Aspects of the Structure of Generic Singularities and Underlying Reasons for that Structure. I'm going to begin with talking about BKL, the B sitting there. You will correct me if I say anything wrong. And also what I call BKL-related behavior, that is spikes that are intimately connected with BKL. Then my talk is in two parts. One is about generic singularities in Bianchi cosmology. One part is about recent developments in GR, and one is about Horava-Lifshitz gravity in Bianchi cosmology. And then the second part here is about some special inhomogeneous solutions and also generic space-like singularities, where I will use this, what I call the conformally Hubble normalized state space approach. I will say a few words about this. And then I'm going to talk about symmetries and state space hierarchies and what I call BKL locality. And then beyond BKL and spikes and what I also call partially local boundaries. So that's the plan. So when you and your collaborators found this BKL chaotic behavior, this oscillatory singularities, one could perhaps take the viewpoint, well, this is just what general relativity is telling you, that this is what you get. But I'm going to argue that there are actually underlying reasons for why you get this particular behavior. That this is intimately connected with the fundamental input you have in general relativity. So this has to do with how symmetries, Keeling vectors, and works, and how you get a kind of hierarchical state-space picture. Then the principles of general covariance and scaling variance induce symmetries on the field equations, which then pushes you to boundaries of boundaries to more and more special behavior, and it eventually actually totally determines the behavior. Symmetries, then I'm talking about Keeling vectors and homothetic Keeling vectors because they are curvature collineations, and they're also Einstein tensor collineations, so they are naturally fit within the scheme of general relativity, in contrast to proper conformal motions, which are not curvature collineations, which therefore you rarely see in general relativity. Then I'm going to talk about the relevance of spatial topology, that spatial topology sets the scene. But later on I'm going also to talk about the irrelevance of spatial topology. The second ingredient apart from symmetries and state space hierarchies is asymptotic causal structures in extreme gravity. That this is intimately tied to why you get BKL and why you get exceptions to BKL. I'm going to talk about vacuum models, but that equally covers, as also already BKL found out heuristically, that you can have perfect fluid as long as you have the speed of sound is less than the speed of light. So for example, dust or radiation. In that case, gravity generates more gravity than matter towards generic singularity. So the matter fields become test fields, and I'm not going to talk about those degrees of freedom, so I'm only going to talk about geometric degrees of freedom here. Then this is tied to asymptotic silence, which is a term I've come up with, which describes that you get particle horizons that shrink towards zero size towards the singularity. But also when you don't have this, a necessary condition is probably to have this in order to have what I call asymptotic locality, which is central for BKL. But also that you can break that and have partial locality. And because of that you have this asymptotic silence, that I'm going to argue makes topological issues irrelevant again. So it's about topological timing. So there's several subtle things here. So what about the generic singularities in Bianchi cosmology? Well, I adapted this talk partly to Mihaly Stefanos, who apparently comes tomorrow. So
he's here.
Oh, there you are. So the first time, this is something that I talked about in the Newton Institute in 2005 when you were there, which I developed over 7 years. And then I wrote up a paper with Mark Heinzler about this in 2010, about how this hierarchical structure you have in Bianchi models, where you get more special Bianchi types as subsets of more general Bianchi types. For example, Bianchi type 9 can be viewed as having subsets of Bianchi type 7, 0, which in turn has a special subset type 2, and so on, by killing structure constants. And in these hierarchies, at each level, the scale invariance group and the automorphism group, that is the special, well, the spatial diffeomorphism group, induce symmetries. They induce monotone functions. For example, scale invariance pushes the most general Bianchi types to the lower next level Bianchi types. And on each level, you get more and more symmetries because you are killing structure constants. And that gives you a bigger and bigger diffeomorphism group. So you get that dynamics is pushed from boundaries of boundaries to more special Bianchi types in this case. And this almost determined asymptotic structure generically. Not almost, because if it was completely, we would have peanuts of proving theorems, and this actually turns out to be quite difficult to prove theorems. In particular, at the bottom of this hierarchy, you have Bianchi type 1 and Bianchi type 2. And those, the solution structure of those Bianchi types is completely determined by the scale automorphism group, that is by general covariance and scale invariance. There's no chance. The solutions can be derived from these principles. This is an illustration of Bianchi type 1 and 2. Here I project the dynamics on the shear, Hubble normalized shear, or if you so want, the trace-free part of the extrinsic curvature divided by the trace of the curvature. Then you get a plane, and in these planes, the Kastner solutions occur as fixed points. And the Bianchi type 2 solutions, they originate from a Kastner point and go to another Kastner point via a heteroclinic orbit, that is a solution that connects two different fixed points. And this is entirely determined by these first principles, scale invariance and general covariance. So you can derive it in this way. And this gives you a map, which you can call the Kastner map or the Bickel map, which describes how you change from one Kastner state to another Kastner state. These are called the tau points, which are special. This corresponds to that you have an LRS symmetry. You have a special symmetry. There's a solution coming from the negative part to that part. But all others go to other Kastner points. So, in my opinion, there are 3 generations of different types of proofs about generic dynamics in Bianchi type 8 and 9. The first generation was done by Hans Ringström around when he was a PhD student already. He showed that part of this Kastner circle, that there are at least 3 points of that is involved in the generic singularity, a non-LRS model, that they have 3 of these points on this circle. And you have to oscillate by these 3 points. And for type 9, he proved that the attractor has to reside on the Bianchi type 1 and 2 subsets. You have 3 type 2 subsets corresponding to axis permutations. So you have solutions coming from this Bianchi type 2, and then you have going like that and that. This is a heteroclinic chain that you can join solutions together. So this is the rigorous dynamical system description of BKL oscillations via Bianchi type 2 solutions in this projection of this shear subspace here. His theorems didn't tell you that you actually follow any of this. It just tells you that you come down somehow. There are periodic orbits here. It could be that we ended up on a periodic orbit. His theorem said nothing about this. So developments sort of stopped when he had done this because people thought we were done, but this was just the first theorems of oscillatory singularity, which was a great achievement. But it was just the beginning what you need in order to have anything that relates to BKL. So in a review, Mark Heinzler and I pointed out something like some stuff of this, and we also pointed out what are the problems to go beyond this, and how would you deal with trying to show that you are in some sense attracted to all of the Bianchi-type 2 sets. Also, he showed nothing about Bianchi-type 8, nor did he show anything, well, except that 3 points here belong to the attractor type 8. Nor did he show anything about causal structure here, which is essential in order to understand BKL. So all of this we pointed out. We also simplified his proof because his proof didn't use these induced structures from the first principles. And if you do that, you could simplify his proof considerably, so we did that as well. But according to several authors now, this paper we did generated new interests, so you got a new generation of proofs, which basically focus on, assume that you are close to one of these chains, and let's perturb along these chains and see what happens. And you got two types. If you stay away from these tau points you have here, then one could show that such orbits, actually, such heteroclinic chains, actually attract a codimension set of one set of solutions of initial data. This was a paper by Beguin and Lipscher, who belongs to a group in Freie Universität. This was later extended, generalized these methods in order to deal with magnetic field, but the important is that they generalized the method so that you could treat a little bit more orbits together with Alan Rendell. Then there is a controversial paper by Reiter and Trubowitz, which showed that, or claimed to show that if you have orbits that don't go too fast towards these messy tau points, which you cannot do in type 9. You can never end up at the local rotational symmetric state. This is also proof by Ringstad. Exactly. And if you don't approach this too closely, too fast, then you would be fine. That you would also have this result in both type 8 and 9, that you end up on the Bianchi type 1 and 2 subsets, all of it, as the future attractor. But no one has been able to prove what they claim. And they haven't published this paper. Then now is what I call generation 3 for several reasons. I was one of the examiners of Hans Ringström for his thesis, and it's fitting that he is now the examiner of Bernhard Brehm at the Freie Universität. Alan Rendell started a project together with Bernhard Fiedler at the Freie University, the dynamical systems group there some 3-4 years ago. And then he left physically and going over to mathematical biology, and he asked me to take over. And I've done that since then. I've been often to the Freie University. And one person there is Bernhard Brehm's student. He has a new thesis, which really should have been posted, possibly is posted today. And he has made tremendous progress by introducing completely new mathematics in this field. And he basically proves that indeed type 8 behaves like type 9, you drop down on the type 1 and 2. But more importantly, he proves that asymptotic silence holds, that you have particle horizons that shrink to zero size that happen, which is what's required in order to prove consistency of BKL in this period. So he's basically proving that BKL is consistent for Bianchi models here. He has also a lot of other work, which we hopefully will publish soon, about the general picture is that there might be a few solutions that don't behave like that, but it seems like every heteroclinic chain attracts codimension 1 set of orbits in both Bianchi type 8 and 9.
Is your student, Brad?
No, he's not my student. He's Bernhard Fiedler's student, but I've been there helping him, and he's working with also Uggla et al., who I'm going to talk about next, who's a postdoc whom I'm working with.
But who is supervisor?
Bernard Fiedler, so a dynamical systems expert. I should also say that you can divide this, that you basically do an analysis close to the Krasner circle, and then you show, after, and this is the difficult part, and then you show what happens afterwards with these Bianchi type 2 orbits. But this local analysis of the Krasner ring here is absolutely central. What about topology in Bianchi cosmology? Well, if you're interested, say, in Bianchi type 9 and 8, they have certain possible topologies. And you might say, we have to keep just looking at such topologies. Well, that would be a mistake. You would never understand them. Because the central building blocks for understanding Bianchi type 9 and 8 here, the generic singularities they have, is Bianchi type 1 and 2 solutions. And they have completely different topologies. So you have to have a rather, once you have determined topology, you have to have a relaxed attitude to topology. The global topology sets the scene, but in order to understand this, how solutions behave, you have to look at solutions with other topologies. There's no chance. This is proven rigorously here. I should say that the role of topology in and its association with the spatial diffeomorphism group in Bianchi cosmology was done when I was a postdoc with Ashtekar and Samuel in '91. For example, in Bianchi type 1, you can't diagonalize Bianchi type 1 if you have certain global topologies, if you want the general expressions. So it affects the degrees of freedom you have, which topology you start out with. But once you have set that topology, then you have to have an open mind for how you are supposed to describe the solutions within that framework you have. In order to understand how these first principles affected, my thought was that you can't just do that in general relativity. In order to understand BKL, in order to understand general relativity, you have to go beyond general relativity. You have to see how these principles work when you tweak them. So I came up with some new models which turned out to be known, called Horava-Lifshitz gravity. And I did this with Uggla et al. At the Freie University in Berlin in this program, which they have there. And this is unpublished. We're still working on it. My motivation was to do something you do in solid state physics, to Lifshitz scalings. So in Horava-Lifshitz, you have preferred foliation. I don't like these models in themselves for several reasons, and NO has several arguments against them. And I agree with them all. But this is not why I was interested in this. I was interested in to see what happens if we continuously deform the symmetries of the coming from the first principles of general relativity. What happens then? Do we get something radically different with BKL? How special is this Bianchi type 1, 2 thing going on? So in these models, you change the kinetic part. GR is obtained by having 1 here, which comes from space-time diffeomorphism. You have the curvature scalar here, which induce this particular form on the kinetic part that lambda is 1. But you can have a generalization, lambda r gravity, where you just let this lambda exist, because if you have a preferred foliation, I can treat an object like the extrinsic curvature, I treat lapse and shift like they were Lagrange multipliers, and then I have a potential part, cosmological constant, plus r, which is in GR, beta is minus 1, plus higher order corrections. This is Cotton-Yoke tensor. This kills chaos, so I'm interested in this part, and it's actually enough to look at lambda r gravity, just generalizing GR with this. What then happens is that instead of having Bianchi type 2 solutions, you have the same Bianchi classifications coming from these particular points, going like that. You move these corners where the straight lines get. You still get from the same principles, which now has been tweaked. Everything. You get the straight lines here, but the straight lines get different directional coefficients here. V equals half, defined by this, is GR. But you can go like this or this. This is what happens when I change lambda here. So we did that. So if we look at the subcritical case, so we go closer, so that vertices are moved here, you get 3 stable sectors in Bianchi type 8 and 9. So from the hyperbolic, transversal hyperbolic is stable, and you might draw the conclusion that all orbits end here. So GR is bifurcation, and you at V equals less than half, you get stable. But that's not true. Well, there is a set of orbits coming from here, this region, which end up at this stable part. So we have to exclude those. They are stable. Are there anything left, possibly coming from here? No. There's a small region here, except though for those that were excluded, that are now excluded. So you cut out the pre-image you get from this. You have to cut out another part, and then another part, and then another part, and then another part, and then another part. Is there anything left? Yes. Counter dust. The situation is precisely like you have for the tertiary counter set. That I remove 1/3 like this, and you get something, and you get just dots here. And when you get a closed set, then it's non-empty. The points are no isolated points, and no interior points. You get this funny counter dust. But this is exactly what you get also in this case. So from a local analysis wouldn't have revealed this. You would have been fooled. So what actually happens, we get a theorem, is that we get a counter set of initial conditions leading to infinite heteroclinic change in a non-empty then counter set. It's of measure 0, so you might be not interested in it, but it's quite funny. You lose all this BKL structure when you do that. You don't have continuous fractions and so on, which is beautiful, all these beautiful things you have in GR, they are all gone. But you can generalize this by using symbolic dynamics. You have to drag in new mathematical tools, which is what we did. And you can go back to general relativity and apply this new tool to relativity, which is what Bernard Brehm has done. And he has come much further because of this. On this counter set, the dynamic is chaotic for this map. So what happens when you have GR? GR is a bifurcation where chaos becomes generic, chaos of these maps. So GR is a bifurcation where chaos becomes generic. Then you can go to the supercritical case. It's even more difficult, and I could really not contribute here. So pure mathematician like Juliette would have to continue on her own here. She used iterated function system where you have 2 unstable modes here towards the past here instead. You still have chaos. You have more chaos than before. But GR is very, very special. So you see that you get all these beautiful structures here. They're all gone if you do these Lifshitz scalings here. And you see that it's absolutely central that you precisely have this general covariance, that you have the scaling variance of relativity in order to get the BKL behavior. You don't get it if you tweak it. Some things remain, but in a very interesting way, but it's different. So let's go to the general cases. So the goal here is very reminiscent of what BKL did, to show that it's possible to construct asymptotics to generic solutions in a neighborhood of a locally space-like singularity. So in order to do this, I have to have certain assumptions that we can foliate this neighborhood with space-like slices that gives you a simultaneous bang function, so that the singularity occurs at a particular time. We assume that the singularity is a crushing curvature singularity, which means that it's going to be associated with a certain scale. And there are tools for this. Your pictures actually cut this thing here. Is what I call that we want to regularize the first order PDE system of Einstein's field equations. And for this, we use something I invented, which I call the Hubble conformal of normal state space approach. So basically, we use the characteristic scale of the expected singularity here, which is the expansion, or if we take a cosmological constant, the Hubble variable. And then we conformally blow up the neighborhood of that singularity by using it as a conformal factor. So you get a conformal spatial tree metric with 3 binds like this, and they evolve according to this equation, where this is basically a time derivative. And one notice that E equal to 0 here, the contravariant spatial method being 0 is an invariant subset, where this is linear combinational connection, Hubble normalized connection coefficients. Then you add Jacobi identities and Einstein's field equations in order to get the first order system of time like PDEs. This is just pure kinematics, so note that there's just one dynamical input I'm really using in order to do this, and that's the Reichauder equation for time like geodesics here, if you want to use conformal geodesics actually. So it turns out that on this invariant subset, which corresponds to setting this metric to 0, if this rank is 0, you get exactly the same equations as you have in Bianchi cosmology, identically the same equations. And it's just there in this state space. This is a kinematic result. The issue is, do you approach it or not? That's dynamics, but it's just there. The difference is here that you have spatial dependence of all the variables. So the state space on this local boundary corresponding to setting this to 0, where you then, because in Bianchi cosmology, of course, when you have this autonormal frame approach, the spatial frame derivatives are 0 by symmetry when they act on connection coefficients, because they only depend on time. So that's why you get the same system. But what happens here then? Well, the constants of integration are replaced with spatial functions on these local boundaries, etc. So this is a precise asymptotically regularized state space which exactly gives you BKL in general. Issue is, does solution approach this subset or not? So why then? It really changes the PowerPoints, this machine a bit. So, well, the picture you usually is that you are supposed to have particle horizons that shrink along towards the singularity here to 0 size. Well, then you can't communicate with your neighbors, so that would explain why you get ODs. This is presumably required to have this BKL locality that you locally can describe evolution by ODEs, coming from Bianchi cosmology, which gives Bianchi cosmology a totally new context. Everything you know about Bianchi cosmology is relevant on the local boundary. So if you want to have an attractor here, it must be the attractor on the local boundary. That's why these theorems by people now on Bianchi cosmology become central for understanding generic singularities, because you have this boundary. So, well, this also seemingly, well, obviously here, if you don't care about your neighbors, well, global topological issues becomes irrelevant. I don't care about them. I'm only caring what happens. This is the only thing that can affect each other here, in this local region here. But on the other hand, global topology will set what degrees of freedom you have from the outside. It will set the scene for the whole business. But once the business is set, it becomes irrelevant locally, if you have a space like singularity. So this gives you a new setting for BKL in the innumerous context, in this infinite dimensional state space. What has happened during the last, well, soon 10 years, is that one has found exceptions to BKL, but they turn out to be intimately connected with BKL behavior. And these are so-called spikes, which I could call, say, asymptotical gravitational defects. Non-uniformities in space, asymptotic. There are several different types of spikes, although there are similar reasons for them. Permanent spikes, but they are non-generic, exact solutions. There are transient spikes, spikes that disappear. They are also non-generic. And then what I claim, infinitely recurring oscillatory transient spikes, which are generic. There are several connections with BKL with these spikes. So one can find, so this is another development, is that one has used solution generating techniques to get the Bianchi type 1 and 2 orbits, but if you continue, you get these other solutions. So they are connected via these solution generating techniques. And it's gone here, but here I said that so far we only have spikes with 2 commuting space-like Killing vectors. Well, until a couple of days ago, when Wei-Shek-Lin and Alan Coley and a student of his published a paper with only 1 Killing vector. By the way, Wei-Shek-Lin is John Wainwright's former student and effectively my former student as well. And he has been working on this since his thesis. I suggested that they would, instead of using methods developed by Randall and Weaver, which was based on method by Vince Moncrief, to use Geroff transformations, because one of the Geroff's solution generators just uses 1 Killing vector, and this turns out to have been the key here. This corresponds to spike crossing. So spikes are surfaces with huge spatial gradients, innumerably described. This is a spike crossing which produces a line. This is for a massless scalar field, so it's not relevant for vacuum here, and this method does not matter, but still it's of interest to have such a solution. The importance of G2's cosmology is analogous with Bianchi cosmology, because you have equations where you can have subsets with rank not just 0, but with rank 1 and 2. And if you have rank 1, you get the G2 equations, but here you have extra spatial dependence, just like you have Bianchi models. And the same for G1. So everything that people have done with solutions with symmetries becomes relevant on these partial local boundaries in the full state space setting of general relativity. This also emphasizes that topology, at least locally, becomes irrelevant, because when you have in G2 you have planes like this. But if you have a local boundary, you have spatial dependence. So then the solutions, so the exact solution has some rigidity, but that rigidity is lost when you view them as on these local boundaries, partially local boundaries. So again, you find new context to previous solutions. Here are examples of special solutions. In a paper we did a fairly long time ago, we looked at exact solutions of different possibilities of asymptotic silence breaking. By the way, spikes, transient spikes, keep this asymptotic silence. You still have particle horizons that link to zero size. So really, those are examples that, yes, this is probably necessary BKL, but it doesn't always give BKL. But it's also of interest to look at models where you break this asymptotic silence. So we went through a bunch of explicit solutions and saw how do they look like. This is an example of a Sekker's dust solution, where you have one part here, which is a violon Kastner pancake, so LRS singularity. Then you have a Ricci-dominated, we call it, if I quote out the symmetry orbits, Lipschitz-Kalatnikov, that is a Friedman model, Friedman evolution, along this line here. But here, you get the Taub-like, again LRS, but with weaker, so here it's a Weyl-Ricci balanced pancake. So you can have very different behaviors. In particular, we looked at several solutions by the previous speaker, and others as well, for weak null singularities. And weak null singularities are typically, for these exact solutions, associated with what I call this Taub subset, which is the Taub form of the Minkowski spacetime. But this belongs to a bigger subset of this partially local subset. And that's where you find, well, so far, all the solutions we have found with weak null singularities, they are connected with this part of the state space, which is the dangerous point in BKL. So you have this solution generating techniques of Rendell and Weaver, Lim apply them. Then you get from Kastner, you rotate Kastner, so you get the gauge transformation. You get Bianchi type 2 from that, you rotate it, and you get what you call a false spike solution. That is a gauge version of Bianchi type 2 that looks like a spike, but which is not. And from that you get spike solutions. But then we did this paper, Mark Heinzler and I, and we asked Wechette to do some numerics for us, where we showed that in the Gaudi models, or the block diagonal case, you have always permanent spikes, and that's what has happened. But they are actually mutilated transient spikes, that is spikes that come and go. Innominaties that blow up and then go back, and you go to the same Kastner state, all of them. Which means that you can concatenate these spikes to infinite spike chains. So you get recurring spike oscillations between different Kastner states. The boundaries, spatial boundaries of these are the BKL solutions. They come from the same solution generating mechanism. And they describe the outer parts of these spikes. You can apply this solution generating technique several times, then you get several spikes, explicit solution. And in principle, you can do it infinitely many times, although not in practice, which would mean solution with infinitely many spikes. I think there are open sets of solutions without spikes, with a finite number of spikes, with a countable number of spikes. Then just a year ago, Wechette used this Gyros transformation to get G2 spikes and showed that these really are. So you got the exact solution describing what we call these transient spikes. But we hadn't published half of the results. We had done a local analysis of the Kastner circle in the full state space and saw that this must happen. And this is what we then found building blocks explicitly to show. So there are intimate connections between BKL and recurring transient spikes via these solution generating techniques then. And I don't think it's sensitive to what techniques you use. I'm sure for the first class you could use the soliton generating techniques. But the advantage with the latter that Gero has is that you only need one killing vector. This is my next to last slide. So you may very well have different solutions with different number of values. One would ask, well, well, in cosmology, what might be enough to have just one spike? If we could observe it, if it left an imprint on large-scale structure, if it could see large-scale structure, then it would be interesting to just have one spike. And Alan Cole and Wechette Lim are looking at such models to see if they can leave observable imprints in cosmology. Remarkably then, there are state-space connections also. So they are associated with this partial local boundary which connects with the BKL at the Kastner circle. So we see them in the state space, in a full relativistic state space. But there are also statistical connections. You go up to that stat space, and I think I see connections with weak null singularities in black holes. This is suggested by the state space picture, but it's also suggested statistically. So statistically, CIA and Lifshitz and others, they showed properties of this BKL map. Oops. And we generalized this to spike statistics. And they all say that the probability is one that you're arbitrarily close to the tau point. And the tau point, already Lifshitz and Kalatnikov in 1962 pointed out that this has to do with caustics. And all these exact solutions which have spatial or just null singularity are on this subset, all of them. So BKL, this is never proved numerically, because numerically it's hopeless to be in this region because it's completely non-hyperbolic. So numerically you are always probing the non-typical region of BKL, never the typical region of BKL. But the typical region of BKL in the statistical sense precisely is that it's almost axisymmetric, almost higher symmetric. And it's directly connected in the state-space part where we see all these weak null singularities. I would be flabbergasted if there was no connection. So in a weak sense here, I would say that BKL, even though there are huge differences, are almost weak null singularities because of this. Because the curvature is as small as possible at this point. You might ask, if you fall in a big black hole, information will not be lost at the horizon. I will scream when I fall into a black hole. Is information coded in these generic singularities? You have an enormous amount of possibilities of coding information. You have an infinite set of heteroclinic change at each spatial point, just for BKL. Then you have the possibility of having spikes, an intersection of spikes. Again, infinitely many possibilities. Is that the way of coding information into gravity, into extreme gravity? I don't know. I don't know why one doesn't pursue it. Also, we find all these relationships via symmetries, with symmetry generating techniques. This must mean that there are hidden symmetries, not just the symmetries I've been able to reveal. 25 years ago, I speculated with Abbe Ashtekar that possibly one could use some of these symmetries, which we were aware of then, but we are aware of many more now, could be used to asymptotically quantize gravity. Since we now know much more, perhaps we are reaching a stage where one can actually use this to go beyond relativity. But that remains to be seen. Thank you for your attention.
Other questions for our speakers, please?
What would be possible observational consequences of the signatures of spikes?
Well, this is what Alan and Coley and Wechett are trying to do, but it's very hard to calculate. I mean, they've been recently found, and there's really no work in this field which has been done, except for a few very simple papers by them.
Okay.
So I think it's an open field.
So would it be a sort of gravitational radiation?
I think that why would you have all these structures if it wasn't for that you have, say, extreme dynamical collisions of black holes? I say if you, I guess analysis is going to tell us tomorrow that it's true that you have a weak null singularity if you non-linear perturb Kerr or something like that, and I totally believe in. But what if you go beyond stationary, almost stationary assumptions? For example, look at criticality. If you just assume stationarity, you would have a Chandrasekhar mass. But then you changed the game completely and you found criticality. You could have infinitely small mass. Why? What are these spikes? I think in the end, I think the solutions are lying to you. Here, things have frozen because of asymptotic silence. And they are more like standing gravitational waves, although this is an extreme gravity regime, so it's very hard to interpret them in that way. But before that, I think they would move generically. So my guess is that they are cranked up versions of gravitational waves. So why would you have that in a cosmological situation at the Big Bang? It would be eminently sensible to have it in black hole formation, where extreme gravity would crank up gravity itself and produce these things under certain circumstances. So I think that it's hard to observe because they might very well be the insides of black holes. That remains also to be seen.
Okay, please.
Okay, you mentioned about the control set.
Yes.
Or the symmetrical control set. Normally we have also so-called non-symmetrical.
This is actually a non-symmetrical counter set. So I took that as a simplest possible example to illustrate the counter set, but this is actually asymmetrical.
Okay.
And it depends on this parameter V, how it's asymmetrical.
Yes, in this case you can apply so-called symbolic dynamics.
Yes, this is what we have done. This is what we were forced to do. And this is what became then useful also in relativity, because it hadn't been used in that way. That's part of Bernard Brehn's thesis. So going beyond GR helped GR in this case.
Oh yeah, thank you very much.
Right, another, yes, please.
You mentioned at the beginning that, well, this is about general relativity, but in fact all of these things follow more or less from general covariance and scaling.
I wouldn't say all of it, but it's certainly there are connections to it.
Okay. So, but I mean, suppose, for example, that I consider a slight tweak where instead of vacuum GR, I put in a massless scalar field. So now things are still scalar invariant and generally covariant, but now instead of all these infinite number of oscillations, as you know, things eventually, leave the Kasner circle and go to a point inside. So how do I know which is the generic behavior? I mean, maybe I should think of the scalar field behavior as this is the general behavior, and it's only in this crazy vacuum case where you don't have a scalar field that you're trapped on the Kasner circle and forced to undergo all these, oscillations.
Yeah. So this is what I had in one sentence and skipped over. I think this is very interesting. So from examples and from heuristic analysis, if you just do this without proofs, you see that it plays an essential role if the characteristics of the matter field are sub-light-like, light-like, or above light-like. And what's more, so if it's sub-light-like, perfect fluids, Blasov, and so on, you get matter does not matter. If it's light-like, matter will matter, and it will matter in an equal way. You have a balanced Ricci-Wild scalar curvature. Singularity. So they balance each other generically. Interesting enough, spin plays a role because spin generates different anisotropies, and that affects the singularity as well. So having a massless scalar field is not the same thing as having an electromagnetic field. It generates electromagnetic field generates oscillations, still balanced with gravity. So they have the same size. But in a different way. So extreme gravity seems to extract the essence of your matter assumptions. If you go beyond the speed of light, information can propagate faster. You get isotropization. So this was shown in a paper using Fuchsian methods by a student, Patrick Sandin and Mike Heinzler, that they generalized the scalar field case, but Lars Andersson and Alan Rendell did to having a fluid with a speed of some bigger than light. And then you get isotropization. And then that means that matter wins over gravity. So equal speed of light, equal effects. More matter wins. Less, harder to affect, gravity wins. That's the basic picture here.
Yes, you have
What do you mean by asymptotic quantization?
So,
Yes.
So we actually suggested several things here. So you have these symmetries. So for example, if you look at billiards like Damour and so, there is a conserved quantity describing generic, say, Bianchi 9 behavior. And it might be that that conserved quantity is enough to get an image product, for example. Then there's billiards. There has been attempts of using these billiards to quantize things before as well. Then, let me take another example. Bianchi 2, which we quantized with geometric quantization EVA, and it's 25 years ago. But if you do a symmetry transformation, you get these false spikes of Bianchi 2. But that, if I do that transformation, I can bring with me all the observables I had for the original case and get a complete set of observables for that type of Bianchi 2, which describes a false spike. So there are several different methods you can do this, and there are several different ways you can use these symmetries. I don't know how far you can push this. I have no idea. But it's clear that you can push it. I don't know how far.
After all, the spikes cannot form the dense set on the singular line. It's correct statement.
I don't know. I think I'm not sure even it's a relevant question. As I said, it might be enough with one spike to be observationally interesting. But as I said, if you apply this solution generating technique infinitely many times, you will get a dense set. You will get a dense set. If you don't apply it, and I don't know if any physical situation corresponds to having the set or not. It might be physically irrelevant that you can do this. It might be more interesting that you have a finite thing for physical reasons, or none at all. That remains to see. But I also think that it's interesting that all these things are intimately connected. This is a clear sign that there are hidden symmetries which we haven't understood. We haven't found them explicitly. And finding them explicitly could very well help to get a complete set of observables, for example. We don't know.
But spatial derivatives in the spike at the singular manifold goes to infinity.
Yeah, you get distributional you get distributional ones, but you could have as a limit at each damned you could still get the damn set on, because the width is exponentially decreasing and becomes zero towards the singularity. It becomes zero, the width of the spike towards the singularity. So you get a distribution asymptotically. It's very subtle.
It's finite time.
Sorry?
It's finite time, aren't they?
If you normalize it, yes. But if you don't normalize it and include the Hubble variable goes to zero, the expansion goes to zero. So if I don't do it, it becomes infinite height. So the physical thing is infinitely high.
But you cannot have 2 points.
I cannot.
Very
I just shown you counter sets and all kinds of fancy stuff here.
Okay.
So I don't know, and as I said, I don't think, my guess is that even if such things exist in relativity, that you have evidence, I don't think that they are physically relevant. So it might be physically uninteresting, but it might very well be very interesting to have a finite set if they corresponds to that this is amplification of gravitational waves in the collapse scenario, for example, if you have extreme dynamical situation that you are far from stationarity and you just graze each other. I don't know. Or if in cosmology they actually can seed structure formation. Because it's quite strange. You get these surfaces, and in the general case, they bend like this. And now we have spike intersections in lines, and you get knots, which we don't have solutions. Very much look like large-scale structure, doesn't it? I don't know if it's relevant or not.
All right, thank you very much. So let's